chapter. Okay, the network analysis. So now the next thing is remaining your inductor. Okay. Visible? Okay, just give me 1 minute. Now, how to deal inductor in the circuit? Okay, so you know what is the sign of inductor? The sign of inductor is this is your L. Okay, so when inductor in the circuit, okay, the voltage, if a current is flowing, okay, time varying current is flowing here. Okay, so the voltage across the inductor is given by L di by dt. If I function of t is flowing in the circuit. Okay. Now the same thing if DC current is flowing. Okay. If I is if DC current is flowing. Okay. If DC current is flowing across the inductor. Okay, then what we can do, we can write di by dt is 0 with the current is DC. Okay, in this case, what will become the V across the capacitor or inductor will become 0. Okay, that means your inductor behaves now short circuit for DC. Okay, so inductor behaves like a short circuit okay for a DC source, for a DC source, for a DC current or DC source, for a DC current. Okay, so that you have to remember. Okay, and one more thing you have to remember here, because there is a L di by dt. Okay, so if you are applying sudden change of current in the circuit, okay, then what will happen? If you are applying sudden current of change, then you require very high voltage to develop, and that is not possible. So like capacitor, yes, the voltage suddenly cannot change. So at t is equal to 0, if you're suddenly trying to push when t equal to 0, you want to see the voltage across capacitor, the voltage is 0. So suddenly it cannot change. So t is equal to 0, capacitor is short circuit, and once it's become steady state, okay, then it's become open circuit. Similarly here at t is equal to 0, your inductor is open circuit, but when you DC apply and that is a stable this stable condition, okay, steady state condition, then you have to replace this inductor by a short circuit. Okay, so for DC source, for DC circuit, DC current, okay, you can replace this, you can short this inductor. Okay, you can short this, so it will be like a short circuit. So short inductor. Yes.
टाइम t इक्वल्स टू 0 के लिए बहुत ज्यादा करंट पास हो रहा है, इसके वजह से वो ब्रेक होता है, इसलिए ओपन होता है क्या?
सडनली DIDT by सडनली 90 डिग्री 1090 है. ओके, स्लोप सडनली चेंज हो रहा है, तो फिर वो उतना वोल्टेज डेवलप नहीं हो पाएगा ना. ओके, तो इसलिए वो ओपन सर्किट की तरह बिहेव करेगा. अगर वो ट्रांजिएंट सर्किट दे रखा है, कोई क्वेश्चन दे रखा है और पूछा है एक स्टडी सेट, तो पूछ लिया, बोले t इज इक्वल टू 0 पे बता रहे हैं, उस समय अगर सर्किट सॉल्व करना है तो इसको आप ओपन करोगे और कैपेसिटर को आप शॉर्ट करोगे. ठीक है. सो नाउ similarly, now if I want to find I in this question, okay, so how to find I? Okay, so this di by dt, okay, so di is 1 upon L v dt. Okay, now कैसे लिखेंगे इसको? सॉल्व करो इसको. If you want to find the current at time t, okay, that will be 1 plus L. Okay, put it minus infinite to t v dt. Okay, and if you want to write here So you can break this limit. So if you want to break this limit, this will become minus infinite to some t0, okay, v dt. And then you can also write, and first you can replace this v by the current also. So if you want to replace this v by the current, okay, so this will become 1 upon L minus t. V is your L di upon dt, okay. So basically what you are left, or let me VDT is random space random. Okay, so minus infinite to t, so 1 by L, okay, minus infinite to t0 v dt plus t0 to t v dt, जैसे पहले किया था हमने. Okay, now you can write 1 upon L, okay, integration t is equals to 0 to t v dt plus 1 by L minus infinite to t0 v dt. Okay. Now here put it it is 1 upon L, t is equal to 0 to t v dt. Okay. Now you have v equals to L di by dt. I, what is this is the equation. So v dt will be your L di. Okay. So you put here 1 by L and you put L, you put here di, and di is from minus infinite to t0. Okay. I'm using this equation from v dt. I'm putting here L di. So here it will come in the form of current at t is equal to 0. So this will be it equals to 1 upon L t0 t v dt. Okay, and this if you put, this will be I at t is equal to t0 minus I equals to t equals to minus infinite. Okay, this will be your equation. It 1 upon L t is equal to t v dt. Okay, and current I is equal to minus infinite. What should be the current in the capacitor, in the inductor? This should be 0. So you can simply write I is equals to I t is equal to 0. So like capacitor, if some voltage is present, okay, you have to count that voltage also. Similarly here, if this current is present in the inductor, that you have to write that current also. Okay, and then it will be 1 upon L. Okay, now you put t is equal to 0, that will be 0 to t v dt. And if you want to write initial time as a t is equal to 0, that will be t is equal to 0. That is your equation. Okay, that is your current flowing at any time t can be calculated using this equation. Okay, in the circuit. So for example, let us do some problem. Please write. So if you return, I can erase this one. Okay. Now suppose a inductor is given whose L value is 5 Henry. Okay, and I'm applying a VT. So VT is 30 t square. 40 is greater than 0 time, and it is 0 t less than equal to 0 time. Okay, now I want to find the current. Okay, current in the inductor at the function of time it. I want to find it. Okay, so what is the formula? The formula is I t is 1 upon L 0 to t v dt. Okay, v dt, and I at t is equal to 0 time. Okay, so t is equal to 0 time, it is given Vt is 0. So, okay, if Vt is 0, so I can write what? The current is also 0. There is no current in the circuit.
2t cube answer.
Huh?
Answer is 2t cube.
T cube V dt. So this is 1 upon L 0. Okay. So it is given. You can write I at t is equal to 0, which is given 0. Okay. So now this will be your 0 t. V is your 30t square dt. Okay. निकालो कितना आएगा?
10t cube by L.
1 by 5, 30 t cube by 3. So 6. This is 2. So this will be current will be 2 at t equal to 0 ampere. The unit is ampere. Okay, shall I rub this one?
Yes, sir.
Yes, sir.
Okay, thank you.
Sir,
Ah,
answer what, sir? 10t cube, no?
2 t cube,
2t.
2 t cube ampere. Okay. Now you have been given a DC circuit. Okay. So all these are what I'm doing. We are solving only DC circuits. Okay, not AC circuits. 1 farad. Okay. This is 2 Henry, 5 ohm, 4 ohm, 1 ohm. Okay. Now you need to find the IL flowing through the inductor. You need to find IL. You need to find what is the energy across capacitor. You want to find the energy stored in the inductor. Okay. So how can we solve this one? Okay. So how should I replace? What should I do now? First thing, as soon as I see the DC voltage, I see capacitor, I have to assume number one thing that capacitor
The
is
2 Henry thing I have to make a short.
two capacitor you have to make open, and this you have to make short. It becomes short. Okay. Now you need to find the current. Okay. No current will be flowing here. Current is going here. 1, 5, 6. I will be what? 12 upon 6. 2 ampere. Okay. So this I will be same like IL. Okay. Now once you know the I, you want to find what is the voltage across this capacitor. Tell me what is VC? What is VC?
We see a 10 volt.
VC will be 10 volt.
10 volt.
Okay. So this current is going 2 ampere. So this 2 volt will be lost here. Okay. 12 minus 2 here you will be having 10 volt. Okay. So whatever voltage here that will come across. So this across 5 ohm, whatever voltage there, that is across the capacitor. So this is your 10 volt. Is that clear? Okay. Now you want omega C. Omega C is what? Capacitor value will be given or not. I gave you capacitor value is 1. Say take 1 farad. Okay, 1 farad. Capacitor value take 1 farad. So half C V square, that is this one, and omega L, half L. L is what? 2 Henry. I is what? 2 to 4. It is 2. This is 4 joule. Omega L. Okay. And here this will be VC will be your 50 joule. So
सर पावर सप्लाई एसी होगा ऐसे क्वेश्चंस मतलब नहीं आते कि
ऐसी क्वेश्चन के लिए आपको पता ही है कि इंडक्टर क्या होता है। इनकी जगह इनका इम्पीडेंस लिखते हैं। ओके, कैपेसिटर का इम्पीडेंस 1/j ओमेगा c लिखते हैं, इसका j ओमेगा लिखते हैं। वो क्वेश्चन आएंगे, वो क्वेश्चन भी कराएंगे ना बाकी।
सर ये VC10 कैसा है तो बता सकते हैं?
किसको?
VC10 वोल्ट।
तो अभी सर्किट में करंट कितना है? 2 एम्पियर है।
यस सर।
ये करंट 2 एम्पियर यहाँ आ रहा है, तो यहाँ पे कितना लॉस हुआ? 2 वोल्ट लॉस हुआ।
यस सर।
बाकी बचा 10 यहाँ पे।
यस सर।
ये 10 पूरा कहाँ है? ये तो शॉर्ट है, 5 ओम के अक्रॉस है।
यस सर।
और यही कैपेसिटर का, ये सेम थिंग कैपेसिटर के अक्रॉस है।
ओह यस सर यस सर।
Now निकालो,
करंट अक्रॉस इंडक्टर निकालना है।
आई निकालना है और आपको सेम VC निकालना है, VC VL निकालना है। ओके, फाइंड आउट द करंट आई हियर। ओके, एंड VC VL you need to find out। तो DC सोर्स है तो आपका ये शॉर्ट सर्किट हो जाएगा। ओके, दिस विल बी शॉर्ट सर्किट, दिस विल बी ओपन सर्किट। 4 फैरेड। बताओ करंट कितना है? व्हाट इज आई वैल्यू?
टू 2.5 एम्पियर।
कितना?
2.5।
हाँ, सोहम कितना आ रहा है? आई
सर निकाल रहा है अभी।
7.5 एम्पियर।
7.5 एम्पियर आएगा।
7.5.
5 एम्पियर, वेरी गुड। सो आई क्या आ जाएगा आपका करंट डिवीजन से? Okay, if you want current, 10 ampere current is coming, that is dividing in this both circuit. Here no current is going, so resistance of this one to total current I, resistance of this opposite branch, and the sum of resistance is 8. So 2 4 2 5 2 2 3 15 upon 2, that is 7.5 ampere. Okay, so here current is 7.5 ampere. This current is going here, 7.5 ampere. So this same current is going here, and that is across the capacitor VC. Okay, so your VC will become 2 into 7.5 ampere, that is equals to 15 volt. Okay, 15 volt का मतलब ये आप एनर्जी निकाल सकते हो। Now omega L half L is 6 I square 7.5 square। Okay, एंड आप ओमेगा C निकालो, हाफ C आपका 4 है, C V
450 जूल।
V कितना है? 15 स्क्वायर। तो ये कितना फर्स्ट कितना आ रहा है? 450 जूल। ओमेगा C 450 आ रहा है। ओमेगा L कितना आ रहा है?
168.75.
168.75 joule. Okay, so this is your answer. Okay, so this was your network analysis DC. Okay, now wherever other things are required for AC circuits, so at that time I will tell you how to do solve the AC circuits. Okay, now wherever required, so this is the basic circuit analysis you should know. Okay, before proceeding further. Now the next chapter. Okay, I'm going to start diode. Okay. Diode and circuit application. Okay, so the diode is basically uh, a PN junction. Okay, so here I'm not going to discuss the PN junction in detail. That I will do when we will study that semiconductor chapter. Okay, so here just I will give you the brief introduction of PN junction. Whatever is required to us for the solve to understand the diode. Okay, so a diode is basically a PN junction. Okay, so you have a P junction and you have a N part. Okay, so basically between the P and N. Okay, so before I understand what is PN junction, let us understand what is P type of P type of this. So this is basically when you bring a P type and N type in contact. Okay, physically in contact. Okay, so not exactly you don't take separate P type and N type and you bring that make a diode. Okay, so suppose you have a N type material and you do doping and the surface you modify with N type of doping to diffusion. So you can create a P type of N type layer. Okay, on same metal. The technique, so the fabrication techniques are different. Okay, so before I say what is P and N, let me tell you what is semiconductor. Okay, so semiconductor. Okay, so semiconductors are two types. One is called intrinsic semiconductor. Okay, and second is your extrinsic semiconductor. Extrinsic semiconductor is two type. One is your P type and one other is your N type. Okay, now intrinsic semiconductor means the pure semiconductor without any doping is called intrinsic semiconductor, while extrinsic semiconductors are the doped semiconductors. Okay. When intrinsic semiconductors are doped with a trivalent impurities. Okay, like iridium, aluminum, third group of element. Okay, then those materials are called p-type material. And similarly, when you dope a intrinsic semiconductor with a pentavalent impurity like your arsenic, antimony. Okay, then these semiconductors are called your N-type semiconductor. Okay. Now, what is the requirement of N-type and P-type semiconductor? Okay. So let us discuss that thing first. So
ट्रीवैलेंट में क्या एग्जांपल दिया गया?
trivalent में aluminium and iridium. Okay. IN, aluminium, arsenic, antimony. Okay. So, okay. So let me give you brief introduction of how to represent p-type material and n-type material. Okay, so now suppose if I have a silicon or germanium. Okay, so we know the silicon and germanium all are tetravalent. Okay, that means in the valence band you have a 4 electron. Okay, they have 4 electron, and these 4 electron they share with the neighboring atoms. Okay, so you have a 1 electron of silicon, this neighboring atom electron. Okay, so you have here also you have 4 electrons. Okay, so 4 electrons. Now these all electrons are in valence band. Okay, valence band means they all electrons are in bonding. So we don't have any. If I say no bond is broken, so at T is equal to 0 Kelvin, okay, we don't have any free electron for conduction. At T is equal to 0, your intrinsic semiconductor behaves like a insulator. So intrinsic semiconductor behaves like an insulator at T is equal to 0 Kelvin. Okay. So now this same thing, if I see an energy scale, so this is my conduction band, and here I have valence band with EV. Okay, so this is the bottom of conduction band EC and the top of the valence band VB. Okay, so all the electrons are present now in the valence band. Okay, and at T is equal to 0 Kelvin, and conduction band is completely empty. So conduction band is empty means you don't have electron for conduction. That means conductivity also 0, like being like insulators. Okay, now this is the this gap is called your EG. Okay, now what you do, now you're supplying some energy. Okay, you're going, temperature is raising above T is equal to 0. Okay, so what will happen, these electron will gain this energy. Okay, these electron will gain this energy, and they will move to the conduction band. So if you have 1 electron here, 1 hole will be here. Okay, so will 1 electron go here, so you have 2 electron here, you have 2 holes here, 3 electron move here, you have 3 holes here. So the number of intrinsic semiconductor, number of electron in conduction band is equals to number of holes in valence band. Okay, and these all electrons are thermally generated. Okay, so you supplying temperature. Okay, so there's a possibility if there is a defect in the system. Okay, some of electron may lie near, some of the energy level of defect may lie in the near the conduction band. That electron can come here, but I am assuming the ideal situation. Okay, so ideal situation, all the electrons are here, you supply the energy, this electron will go here, and the number of electrons is number of conduction band. Now in order to make intrinsic semiconductor conducting, okay, you require high temperature. Okay, so suppose you require high 100 degrees centigrade, 200 degrees centigrade temperature. Okay, so that these kind of semiconductor are not useful for practical applications where you are working on at room temperature, or sometime that countries where temperature is well below 45 degree, you're working at a very lower temperature. So you need a semiconductor which has a conductivity which we require for the operations. Okay, so that's why what we do, in order to increase the conductivity of these kind of semiconductor, we do the doping. Okay, and once we do the doping, we get the extrinsic semiconductor. Okay, now let us discuss what is p-type and n-type semiconductor. Okay, so if this silicon in the system, if it is replaced by, say, called your arsenic. Okay, arsenic has 5 valence electron, so out of 5 this will share the 4 electron of the neighboring atoms, and it has a 1 electron left here. Okay, so this electron, because when you introduce the impurity, and if I, so suppose this is I call this the n-type material. Now, where is this electron? Okay, these are bonding electrons. Bonding electrons are in valence band. Okay, and so where is this electron? Okay, so with this electron, if you see, so this is your conduction band, and this is your valence band. This is your EC. This is your EV. Okay, the energy level of this impurity, what you introduce in the system, that lies somewhere near to the conduction band. Okay, so these are the impurity arsenic levels. Okay, and we call them as a donor level. ED is donor level.
Sir, can you repeat?
I'm saying the impurity what you have introduced in the system, okay, crystal, okay, that has an energy near to the conduction band. Okay, so you can say all the arsenic atoms or all the, so this I call it donor level, but because this electron is giving this electron to the system, so this is a donor. Okay, so donor level, so all arsenics are sitting here, arsenic atoms are sitting here, is all arsenic atoms are sitting here. Okay, how much number you are doping, that depend how much percentage you are doping, whether you're doping 1% you are doping, or you're doing 0.1%, 2%. The amount of doping, okay, decides how much the conductivity you get with this kind of systems. Okay, so when you're doping arsenic, okay, what will happen? This arsenic, now this level is very close. Okay, and this arsenic can be ionized very easily, because it has an electron, and this electron is very near to the conduction band. If you supply little bit energy, okay, so this arsenic atom will ionize. Okay, and they give up their electron, and their electron is very near to the, this is reached to the conduction band. Reaching to conduction band, now it become free. Now it is not located, now it is not bound to this arsenic, or not, it not belongs to the arsenic. Okay, it can roam in the crystal freely. That's why we say it is a conduction band. So now you don't require that much energy. If you want to bring this electron into the conduction band, okay, so these electrons require very high energy to reach from here to here. Okay, so that not possible at room temperature or at lower temperature, but these electron can be ionized very easily, so you get the conductivity. That's why the external semiconductor have very high conductivity. So n-type semiconductor, so n-type material has majority charge carriers as an electron. Okay, so majority charge carriers in n-type. Okay, this, and I'm discussing n-type full now, n-type. So n-type majority charge carriers are electrons. Okay, now there's a possibility when some temperatures, some of electron, sometimes some of these electron also can come here, join here, but their number will be very less. Their number will be very less. Okay, and so you can create some holes also in n-type material. So the holes will be your minority charge carriers. It will be minority charge carriers are holes.
Sir,
Ah.
we get this at temperature greater than 0, na?
Yes, ये हाँ,
हाँ, ये
of course temperature greater than 0 होना चाहिए, otherwise ये भी तो ionize नहीं होंगे ना.
हाँ.
But you require 0.01 or 0.1 electron exactly, I don't remember, but less energy you require, okay, to move from here to here. So now,
Sir, they require high amount of energy to transfer these electrons to conduction band. Why, sir?
which electron?
Valence band electrons, sir.
Which one?
Valence band electrons.
Valence band require more energy. You see, more gap is there, na?
Okay.
And this gap is less, you will require less energy.
Okay.
Okay. So now,
Sir, मतलब वाइवा में we used to be asked, sir, how do we used to doping means का कोई अलग से process होता है?
there are many processes are there. This fabrication process are there.
Oh,
Okay, if you've done the semiconductor course, there's a diffusion process, ion implantation, both chemical techniques भी होती हैं.
oh,
There are
okay,
variety
sir.
technique where you can dope the material. Okay.
Okay, sir.
Now, the n-type material. Okay. So n-type material, generally we represent n-type material by donor atom, and donor atom is positive charge. Positive charge means once it gives the electron, it will become positively charged. Okay, so if I want to represent an n-type material, this is my representation of n-type material. So this is n-type material. So this is the electrons, okay, free electron which can move, free electrons, okay, and this is the immobilized ion, immobilized ions, okay, which cannot move, okay, and this is your n-type. Okay, now similarly, either you can represent n-type material by this type of schematic, or you can represent n-type material by just showing the presence of majority charge carriers. Okay, so either you represent like this, or either you represent this like, okay, this is a standard way of representing any n-type of material. Clear?
Yes, sir.
Now next
ये
is
दूसरा क्या बताया था?
कौन सा वाला? ये वाला,
एक फ्री इलेक्ट्रॉन था और एक दूसरा था।
ये तो immobilized ions, मतलब ये लैटिस के अंदर है, तो एटम है, तो ये तो आयनाइज
ओके
करेंगे नहीं, तो ये तो लैटिस में फिक्स है, तो ये उसका इलेक्ट्रॉन जो फ्री हो सकता है एनर्जी देने पे, एंड दीज आर द इलेक्ट्रॉन्स, ओके, these are majority charge carriers, majority charge carriers, these are electrons. Now let us discuss p type of material. You remember the schematic what I would drawn, okay, and type material, that schematic I will use. Okay, we'll discuss more detail when we discuss semiconductor. Okay, for the moment I am just discussing this one. Okay, so now this is your p type material. Okay, p type semiconductor. तो p type of material क्या हो जाएगा आपका? p type material में you have, suppose मैं सिलिकॉन का एग्जांपल ही ले रहा हूँ. So silicon, again it has a 4 electrons, 4 electrons, 4 electrons, 4 electrons, 4 electrons, 4, 4, 4, 4, 4. Okay. Now if I dope, okay, if I do doping, here itself I'm doing doping, okay. If I replace, say, this by aluminium, so aluminium has only 3 electrons valence band, so it can share 3 electrons. So 1 electron, these has a 1 electron less, okay, compared to the silicon. So here we have one hole present here. Okay. Now what do you meaning by hole present? Okay. Let us discuss it. This in energy diagram. So this is your p type.
Deficiency of electron.
Okay. Or deficiency of electron. Okay. So hole. This is the deficiency of electron. So now this is my semiconductor conduction band, valence band. So p type of materials are those material whose energy level generally taken or lies near the valence band. Okay, and these are the acceptor ions. So this is the aluminium, aluminium, aluminium. Okay, aluminium. So what these electron can do? These electron can come here. Okay, 1 electron can come here, and this aluminium can accept this somewhere from here. 1 electron can come and fill this gap. Okay, so these ions are basically acceptor ions. So the electron can jump here from here to here, and somewhere there will be more hole. So electron can move from one hole to another hole. Okay, so it should look like a electron is moving, and opposite to this is the hole is moving. Okay, so this will whatever here is electrons are there, valence band of silicon. These electrons can come here, and this can become negatively charged. Okay, once these electrons come here, suppose 4 electrons are coming. 4 electrons are coming, so you have a 4 holes here. Is electron go here, electron goes here, electron goes here. Okay, so you get 4 holes here. So now your p-type material majority charge carriers are whole. Okay, here it is, here it is empty. Okay, at low temperature, there's a very less possibility that this can go here. So only you have now holes in the valence band. So your majority charge carriers are whole. Majority charge carriers are holes. Okay, in p-type semiconductor. Now how to represent p-type semiconductor? P-type similar. हाँ बोलो.
तो यहाँ होल कंडक्शन बैंड में मूव होते हैं क्या बाद में?
होल थोड़ी कंडक्शन में होता है. होल हमेशा वैलेंस बैंड में होगा.
तो यहाँ कंडक्शन मतलब यहाँ इस डायग्राम में तो कंडक्शन बैंड में कुछ नहीं है ना?
कुछ नहीं है ना.
तो कंडक्शन कैसे?
बट होल्स यहाँ पे तो मेजॉरिटी चार्ज के तो होल है ना. होल्स मूव कर रहे हैं ना. होल्स तो मूव कर रहा है. ओके, ये इलेक्ट्रॉन यहाँ से देखिए यहाँ पे जंप कर रहे हैं. ओके, तो ये वैलेंस बैंड से इलेक्ट्रॉन जाके यहाँ पे जंप कर रहे हैं, इसमें मूव कर रहे हैं. ओके, तो ऐसा लग रहा है कि होल्स मूव कर रहे हैं. ठीक है.
सर इसमें मतलब बी टाइप में कंडक्शन बैंड में चाहिए मतलब होल्स कैन मूव इन द
पी टाइप की कनेक्टिविटी दो तरह से होती है. एक होती है इलेक्ट्रॉन के कारण, एक होती है होल्स के कारण. पी टाइप की जो कनेक्टिविटी होती है वो खाली होल्स की वजह से होती है.
that would be in valence band.
That is in valence band. So here this will be your, here will be hole, 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 here will be hole. So वैसे भी जैसे भी शेयरिंग में आता है. ओके, सो दिस विल बिहेव लाइक अ, क्योंकि इसको ये इसका इलेक्ट्रॉन मिल रहा है ना, इसका इलेक्ट्रॉन मिल रहा है, तो ये क्या है, इसके तीन इलेक्ट्रॉन का यूज हो गया है, तो ये हमेशा नेगेटिव चार्ज ही रहेगा. ओके, ये नेगेटिव चार्ज रहेगा. तो और ये होल इसके पास में हमेशा रहेगा. तो दिस इज द रिप्रेजेंटेशन ऑफ ए पी टाइप मटेरियल. ओके, पी टाइप मटेरियल. सो दिस इज द एक्सेप्टर इमोबल एज आयन. दीस आर एक्सेप्टर आयंस. Acceptor ions. Okay, and these are holes. Okay, this is the p-type material.
सर तो इसमें कंडक्शन कैसे हो रहा है? कंडक्शन बैंड में तो गया ही नहीं सर.
वैलेंस बैंड में होल्स मूव कर रहे हैं.
ओ तो कंडक्शन हो गया.
इलेक्ट्रॉन के कारण नहीं हो रहा, होल्स के कारण हो रहा है. कनेक्टिविटी होल्स के कारण है. होल्स को एक एनर्जी लेवल मिल गया ना मूव करने के लिए. होल्स को एक एनर्जी लेवल मिल गया मूव करने के लिए इधर. ओके, या तो यहाँ पे एनर्जी लेवल फ्री हैं, यहाँ पे भी मिल गया उसको, एक होल मिल गया, तो इट कैन मूव थ्रू दिस लेवल्स. ओके, तो नाउ
मूवमेंट से यहाँ करंट जनरेट हो रहा है ना
हाँ?
सर. होल्स मूव हो रहे हैं, इसके वजह से करंट जनरेट हो रहा है ना, इसलिए हम कह रहे हैं ना कि कंडक्शन.
हाँ, होल करंट जो है होल करंट है. ओके, दिस इज योर पी टाइप. इसको हम डिटेल में बाद में करेंगे. अभी हमको जो चाहिए सेमीकंडक्टर के लिए उतना हम बात कर लेते हैं. ओके, दिस इज माय पी टाइप मटेरियल. ओके, सो लेट मी draw this p type material again here. So this is my p type material. Here you have hole. Okay. And here you have, say, a N type material. Okay. P and so you have electrons here. Now what you do, you bring these two section of, okay, you are bringing two section in contact. ये समझने के लिए एक्चुअली में तो एक ही मटेरियल में डिफ्यूज करके एक हिस्से को पी टाइप बनाते हैं, एक को एन टाइप रहने देते हैं. ओके, तो एक पी टाइप लेते हैं, उसमें डोपिंग करते हैं, दूसरा एन टाइप बन जाता है. पहले कोई इंटरेस्ट नहीं लेते हैं, उसे पी टाइप डोप करते हैं, पी टाइप हो गया. तो इसके ऊपर और इसमें एन टाइप इनपुट डिफ्यूज करते हैं, तो एक पीएन जंक्शन बन जाता है, पीएन जंक्शन बन जाता है। ओके, बट अंडरस्टैंड करने के लिए फिजिकली मैं इसको अलग बता रहा हूँ। नाउ फिजिकली आई विल ब्रिंग दिस टू सिस्टम टुगेदर इन कॉन्टेक्ट। तो कॉन्टेक्ट पे क्या होगा, कॉन्टेक्ट पे क्या होगा, जैसे ही इनको ब्रिंग करेंगे तो इसमें क्या होगा, डिफ्यूजन होगा, क्योंकि बिकॉज वेयर एवर कंसंट्रेशन मोर, जैसे इलेक्ट्रॉन की कंसंट्रेशन ज्यादा होगी तो इलेक्ट्रॉन concentration will move from higher to lower concentration. Okay, or oppositely you can say if holes are more in some place, that will move on the other side. Okay, so basically तो इलेक्ट्रॉन ही मूव करते हैं, तो when I bring this two system in contact, what happen, these electron will move here. Okay, so यहाँ पे मूव करेंगे तो क्या होगा, इस होल से रिकम्बाइन हो जाएंगे. Okay, so they will recombine with these holes. Okay, so when I bring this PN junction, I form PN junction, what will become, because of this concentration gradient, some of my ions will ionize. So say this, ये मेरा ionize हो गया, ये मेरा ionize हो गया, ionize आके प्लस बन गया. Similarly ये जो नियर बाय कॉन्टेक्ट पे है, ये मेरा ये इलेक्ट्रॉन यहाँ चला गया, ये न्यूट्रलाइज हो गया, ये नेगेटिव चार्ज हो गया. ठीक है, तो ये क्या हो गया, अब यहाँ पर तो सिस्टम सेम है, यहाँ पे तो आपके पास में सपोज दो लेयर आयोनाइज हो गया, एंड हियर दो लेयर आयोनाइज हो गया. So this region is called your, now this is your p type, which has a majority charge carrier hole, and here you have n type where majority charge carrier is electron. इंटरफेस पे ये जो हो रहा है सब इंटरफेस पे हो रहा है. ओके, तो धीरे धीरे चार्ज इलेक्ट्रॉन जाएगा यहाँ पर, तो यहाँ पे क्या होगा, एक इलेक्ट्रिक फील्ड डेवलप हो जाएगा, और इस इलेक्ट्रिक फील्ड के कारण क्या होगा, इसकी डायरेक्शन प्लस से माइनस की तरफ होगा. ओके, तो इनबिल्ट इलेक्ट्रिक फील्ड डेवलप हो जाएगा डिप्लेशन रीजन में. अब अगर ये दूसरा इलेक्ट्रॉन यहाँ जाना चाहता है, तो ये इलेक्ट्रिक फील्ड जो स्टडी स्टेट में जब ज्वाइन कर रहे हैं, ऐसा नहीं है कि सारे इलेक्ट्रॉन यहाँ से उठ के यहाँ चले जाएंगे. जैसे जैसे इलेक्ट्रॉन यहाँ लीव करेंगे, ओके, यहाँ पे एक स्पेस चार्ज क्रिएट होगा, that space charge will create an electric field. Now further electron cannot come here, so here your material is like n-type with majority charge carrier electron, here material is p-type with majority charge carrier holes. Only interface, okay, interface you have in contact, you have developed a space charge region. Okay, and this space charge region is called depletion region. Okay, now because there is separation of charge carriers, okay, that means there is the barrier also. So if I draw the potential barrier, okay, so at this side to this side at interface, okay, so there is a potential barrier of this one. Okay, so this is your p side, this is your n side. So between at the contact you have potential difference, because you have a potential, one side potential is Vn, other side potential is say Vp at the boundary. And because there is a potential, because there is electric field, there is a potential. Okay, the slope of the slope dv by dx, so E is what, E is minus dv by dx. Okay, so because there is electric field in this depletion region, and that is this depletion region is free of charge carriers. Okay, so no charge carriers present, no charge carriers present. No free charge carriers present. Okay, no free charge carriers present. Okay, in the depletion region. This is one thing. Okay, now second thing is what? So this electric field is because of bound charges. Okay, these charges are not free, so you cannot measure physically this potential difference. Okay, if you want to you put a voltmeter here and you say because the potential is there, I want to measure the potential, but potential you cannot measure. Okay, potential you can only measure because of free electrons. Okay, here you have bound charges, so this potential difference you cannot measure with a normal with voltmeter. Okay, so now this is the barrier. Now if I want to say the energy is your QB. If I want to write the electron energy EV, electron is a minus charge. Okay, so if I want to draw an electron energy levels, okay, that is EV, that will be opposite to this one. Okay, that will be opposite to this one. So let me first discuss व्हाई दिस डिफ्यूजन इज टेकिंग प्लेस, ओके।
सर इलेक्ट्रिक फील्ड का डायरेक्शन सही है और जो
इनबिल्ट तो सही है ना, प्लस से माइनस की तरफ होगा इलेक्ट्रिक फील्ड तो हमेशा ही। तभी तो इलेक्ट्रॉन यहाँ से इलेक्ट्रॉन पे फोर्स का लगेगा, ये इसको होल को यहाँ आने नहीं देगा, एक तरह से समझो, और ये इलेक्ट्रॉन को यहाँ से जाने नहीं देगा, ये रिपेल करेगा, ठीक। ये इलेक्ट्रॉन यहाँ नहीं आ सकता क्योंकि अब फील्ड डेवलप हो गया, ओके।
जो
सर,
पॉजिटिव और नेगेटिव हमने बना के रखा है सर, ये क्या है?
ये आयन है ना, ये आयोनाइज हो गया ना, ये चार्जेस है। तो ये एक तरफ प्लस चार्जेस है, एक तरफ माइनस चार्जेस है। तो प्लस चार्ज मतलब जैसे कैपेसिटर में क्या होता है, एक में प्लस चार्ज होता है, एक माइनस चार्ज होता है
जी।
तो वैसे ही सिस्टम, वैसे कैपेसिटर टाइप का सिस्टम बन गया यहाँ पर,
इंडक्शन की वजह से हो रहा है यहाँ पे।
डिफ्यूजन की वजह से। डिफ्यूजन हुआ, डिफ्यूजन हुआ, कंसंट्रेशन ग्रेडियंट के कारण ये लीव कर गया है, ठीक है।
तो वहाँ पे कोई चार्ज ही नहीं होगा तो इलेक्ट्रिक फील्ड भी नहीं होना चाहिए ना सर।
कहाँ पे
डिफ्लेशन लेजर
चार्ज तो है ना,
सारे तो न्यूट्रल हो जाएंगे ना सर।
सेपरेशन तो है ना चार्ज कैरियर्स में, सेपरेशन तो है चार्ज कैरियर्स में। ये अगर मैं यहाँ पे एक चार्ज पॉजिटिव रख दूं, एक चार्ज नेगेटिव रख दूं, तो दोनों तो जीरो है, लेकिन कुछ इसमें देखो डाइपोल मोमेंट तो होता ही है, इनके बीच में इलेक्ट्रिक फील्ड तो होता ही है, फोर्स तो होता ही है, नहीं।
सर लेकिन ये यहाँ क्लोज है ना, मतलब सरफेस पे है।
इफेक्टिव तो सेपरेशन है, बिल्कुल एकदम थोड़ी जुड़े हुए हैं, सेपरेशन तो है ही ना, इफेक्टिव सेपरेशन तो है ही ना, इफेक्टिव सेपरेशन तो है ही दोनों में, ओके। तो कैपेसिटर में क्या होता है, कैपेसिटर में भी तो ये होता है, कैपेसिटर में फील्ड नहीं होता क्या, कैपेसिटर का फील्ड क्या होता है, प्लस प्लस माइनस माइनस, ई इक्वल्स टू क्या होता है कैपेसिटर पे, V बाई डी। तो कैपेसिटर में भी कोई कोई एकदम ये अलग अलग थोड़ी होते हैं, क्या थोड़ी होता है, यहाँ पे कोई डाइलेक्ट्रिक मटेरियल होता है, डाइलेक्ट्रिक होता है, वो डाइलेक्ट्रिक पोलराइज होता है, when you apply इलेक्ट्रिक फील्ड, ये प्लस है तो यहाँ पे ये डाइपोल्स बन जाएंगे when you apply फील्ड, ओके। और फील्ड के कारण क्या हो जाएगा आपका, यहाँ पे इलेक्ट्रिक फील्ड क्रिएट हो जाएगा, बढ़ जाएगा। so there's a so there is a electric field, okay। now let me draw these things in different way, okay। now what is meaning of this p-n junction, so if I say my p type of material, okay, so p type material में क्या होता है, this is your conduction band EC, this is your valence band, okay। here you have acceptor level and the Fermi level of Fermi level of p type material also is close to the valence band, okay। and if you have studied in your school or colleges, if you say n type material में आपका Fermi level यहाँ पे होता है, close to conduction band होता है, तो EFN and this EFE, okay। so whenever I bring two things in contact, तो contact पे क्या होगा, now current क्यों flow होता है, current जैसे एक वायर है, okay। अब इस वायर पे मैं वोल्टेज लगा रहा हूँ तो करंट क्यों फ्लो होता है, करंट फ्लो होता है क्योंकि हम कांटेक्ट में जो मटेरियल है इन दोनों के बीच में फर्मी लेवल में डिफरेंस क्रिएट करते हैं, ओके। फर्मी लेवल में डिफरेंस क्रिएट करते हैं, जहां पे इलेक्ट्रॉन होते हैं, यहाँ से इलेक्ट्रॉन का माइनस चिन्ह तो इलेक्ट्रॉन का एनर्जी अप हो गया और होल्स का डाउन हो गया। सो इन दोनों के कॉन्टेक्ट में हम डिफरेंस क्रिएट करते हैं, इसीलिए क्या होता है कि इलेक्ट्रॉन मूव्स फ्रॉम हायर लेवल टू लो लेवल, सो दैट्स व्हाई दिस लेवल इज हाई, दिस लो, सो इलेक्ट्रॉन मूव्स लाइक दिस, and when electron moves like this we say current is moving like this, okay, applying voltage. So the basic the thing I want to tell that one material cannot have a two Fermi levels, okay। so when I bring these two material in contact they should have a one Fermi level, okay। and one Fermi level कैसा होगा, one Fermi level होगा जैसे ही हम इसको लाएंगे तो डिफ्यूजन हो रहा था, तो डिफ्यूजन होने से क्या हो रहा था, ये इलेक्ट्रॉन जंप कर रहे थे इधर, सो जब भी इलेक्ट्रॉन एन टाइप पे कम होते हैं तो वो नीचे आता है और एफ, और यहाँ पे जितने भी होल कम होंगे, यहाँ पे जितने भी होल्स को ये रिकम्बाइन करेगा इलेक्ट्रॉन से, तो वहां पे क्या होगा, इसका फर्मी लेवल क्या होगा, ऊपर जाएगा। सो एट द कॉन्टेक्ट व्हाट हैपन, एट द कॉन्टेक्ट दिस काइंड ऑफ थिंग्स हैपन्स, ओके। ये खाली कॉन्टेक्ट का एनर्जी डायग्राम है, ओके, पीएन जंक्शन के कॉन्टेक्ट का। तो कॉन्टेक्ट पे क्या होगा, फर्मी लेवल सेम हो जाएगा, ओके। अब वो क्या हो जाएगा कि चार्ज सेपरेशन हुआ, इलेक्ट्रॉन मूव करे तो अब क्या हो जाएगा यहाँ पर एक तरह से, क्योंकि इलेक्ट्रॉन का एनर्जी लेवल नीचे आएंगे, क्योंकि इलेक्ट्रॉन कम हो रहे हैं यहाँ से, इलेक्ट्रॉन यहाँ से जा रहे हैं होल में, ओके, होल्स से इलेक्ट्रॉन कंबाइन कर रहे हैं, तो यहाँ पे होल्स कम हो रहे हैं, तो ये अब पी टाइप नहीं रह जाएगा मटेरियल, थोड़ा सा इसका ये थोड़ा सा इंटर्नशिक की तरफ जाएगा, इसलिए यहाँ पे इलेक्ट्रॉन कम हो रहे हैं, तो ये भी थोड़ा इंटर्नशिक की तरफ जाएगा। इंटर्नशिक में फर्मी लेवल बीच में होता है, ओके। सो दिस काइंड ऑफ बैलेंस पोटेंशियल डेवलप एंड दिस गैप इज कॉल्ड QBBI। अब इसको हम बाद में डिटेल में डिस्कस करेंगे, अभी मुझे सब इसका खाली थोड़ा सा एक चीज चाहिए, ओके। तो दिस इज QBBI, सो दिस इज योर EC, दिस इज योर EB ऑफ पी टाइप मटेरियल। हाँ बोलो, EC
होल इलेक्ट्रॉन होल के लेवल में जा रहा है,
हाँ,
मतलब नंबर ऑफ होल्स भी कम हो जाएंगे।
होल्स भी कम हो जाएंगे,
लेवल ऊपर कैसे आएगा सर? एनर्जी तो
होल्स कम हो जाएंगे भी। इंट्रिंसिक में फर्मी लेवल यहाँ होता है, जब आप उसमें एन टाइप डोपिंग करते हो तो फर्मी लेवल ऊपर जाता है, जब उस पर आप पी टाइप करते हो तो फर्मी लेवल नीचे जाता है, ओके। ये डिस्कस करेंगे बाद में हम लोग, ओके। अभी बस इसको समझ लो, इसको याद रख लो। तो जब भी हम पीएन जंक्शन बनाएंगे तो पीएन जंक्शन पे क्या हो जाएगा, एक तरह का बैरियर क्रिएट हो जाएगा। दीज आर द एनर्जी लेवल्स ऑफ इलेक्ट्रॉन। पोटेंशियल कैसा था, पोटेंशियल ऐसा था, पोटेंशियल ऐसा था, और एनर्जी लेवल कैसा होंगे, उल्टा, इसका उल्टा, क्योंकि इलेक्ट्रॉन के एनर्जी लेवल्स हैं, ओके। सो QEEV, सो नाउ इस तरह का एक बैरियर क्रिएट हो जाता है व्हेन यू मेक ए पीएन जंक्शन, ओके। सो पोटेंशियल डिफरेंस आ जाता है। सो यू हैव अ पीएन जंक्शन हियर, is the P type material, your N type material, and here you have space charge region, और इन दोनों के बीच में एक पोटेंशियल डिफरेंस है, ओके। दिस इज पोटेंशियल डिफरेंस, जिसका इलेक्ट्रिक फील्ड इस डायरेक्शन में है, ओके। नाउ what happens if I apply a forward voltage here? If I apply a forward voltage here, VF, okay, this is an equilibrium, this is equilibrium, this is the band diagram of contact. Now when I apply forward bias voltage, this voltage, external voltage, this will create an external field. This external field will be opposite to this internal field. So what will happen, because of this external voltage, what will happen, this barrier height will decrease slowly depending how much voltage you are applying. अभी voltage इतना है, okay, built potential, and बाद में क्या हो जाएगा, अगर आप VBI के बराबर पोटेंशियल लगा दोगे, ओके, तो ये एनर्जी, तो ये गैप कम हो जाएगा, and they will come same level and the current can flow, okay. So now if I apply voltage, so this voltage is opposite to this built-in potential, so what will happen, you will have voltage now, instead of Q built, you have a QB VF, okay. Similarly, this energy, this barrier height will decrease, okay, barrier height will decrease, and if you apply, तो मिनिमम इतना वोल्टेज लगाना ही पड़ेगा डायोड को कंडक्ट करने के लिए, इस पीएन जंक्शन को करंट को फ्लो करने के लिए इस बैरियर को हटाना पड़ेगा, ओके। तो मिनिमम वोल्टेज ये चाहिए हमको, इससे ज्यादा लगाओगे तो फिर क्या हो जाएगा, यू हैव कंडक्शन, ओके, यू विल गेट द करंट फ्लोइंग इन द पीएन जंक्शन, ओके, एंड दैट इज कॉल्ड योर डायोड करंट, ओके, दैट विल बी योर डायोड करंट। सो फॉरवर्ड बायस आपका पीएन जंक्शन कंडक्ट करेगा। नाउ व्हाट हैपेंस इन रिवर्स बायस, so this is forward bias, so your forward bias, okay. Now similarly if I take a reverse bias, okay, so reverse bias में क्या हो जाएगा, you have this PN junction here, okay, plus minus, okay, this P is N, and now you apply reverse bias, मतलब P को नेगेटिव से कनेक्ट करो, N को पॉजिटिव से कनेक्ट करो, okay. So this is your reverse bias, okay, this is plus minus, plus minus. Now this electric field will be, external electric field will be in the same direction of internal field in the space charge region. So what become, this height will increase, this barrier height will increase, okay. So this barrier height will now increase, okay.
Sir, last statement, can you just repeat, sir?
The external field is now in the same direction of internal field, okay. So this is your ECP, this is your EVP, okay. अब मैंने यहाँ प्लस कर दिया इलेक्ट्रॉन पे, तो इलेक्ट्रॉन के एनर्जी लेवल डाउन होंगे, ओके। So now when there is a equilibrium, they at the contact they have a same Fermi level. Now what will happen? The Fermi level will come down and holes will go up. Okay, holes will Fermi level p type will go this one. So this is now your EFP and this is your EFN. Okay, and this gap is further. This gap is equals to what you're applying QVR. So this gap is increased. It's become now QVBI plus VR. Okay. So you don't need to only understand one thing. Whenever I will apply forward bias, my barrier height will decrease and current will flow. And whenever if I apply reverse bias, this barrier height will increase. Okay, and only a little bit current. Okay, that is called reverse current will flow in the circuit. So this will be reverse current, and this will be your forward current. It will be a reverse current, and this is your forward current. Okay, that will be flowing in the circuit. Okay. हाँ
मतलब ये समझ में नहीं आ रहा है, फॉरवर्ड बायस में करंट जो हमारा इलेक्ट्रिक फील्ड है उसके अपोजिट में हम इलेक्ट्रिक फील्ड अप्लाई कर रहे हैं।
तो वो बैरेट तो वो अपोजिट में बैरेट को कम कर रहा है, हाइट को। अभी इलेक्ट्रॉन मूव नहीं कर सकता ना,
हाँ
बैरेट हाइट कम कर देगा तो इलेक्ट्रॉन कैन इजीली मूव।
हाँ, मतलब वो इफेक्टिव वो जो इलेक्ट्रिक फील्ड है उसको रिड्यूस कर रहा है।
रिड्यूस कर रहा है, बैरेट हाइट को कम कर रहा है। सो अभी तुमको इतना याद रखना है कि आपका जो फॉरवर्ड बायस है उसमें वोल्टेज का ये बैरेट कम हो जाएगा, इतना याद रखना है। रिवर्स बायस में बैरेट हाइट हो जाएगा। रिवर्स बायस में जो करंट फ्लो होगा यहाँ से लेके उसको बोलेंगे रिवर्स करंट। फॉरवर्ड बायस में जो करंट बोलेंगे उसका फॉरवर्ड करंट। और इनका जो फॉर्मूला है करंट का, ओके, ये याद रख लो। दैट इज द करंट इज गिवन बाय डायोड, करंट फ्रॉम डायोड इज गिवन बाय IS exponentially, okay, QV upon KT minus 1. okay, ये फैक्टर ईटा का भी होता है, वही पे लिख नहीं रहा हूँ। आइडियल के लिए ईटा इक्वल टू 1 ले लेते हैं आइडियल डायोड के लिए। तो दिस इज फॉर आइडियल डायोड, दिस इज फॉर आइडियल डायोड, ओके, where IS is your reverse saturation current, your reverse saturation current, okay. V is the applied voltage, V is your applied voltage, okay.
के बाद क्या लिखा हुआ सर? QV अपन
KT टेम्परेचर।
ये करंट का एक्सप्रेशन सिर्फ रिवर्स बायस के लिए है ना?
नहीं, ये दोनों के लिए, रिवर्स बायस के लिए भी, फॉरवर्ड बायस के लिए भी है। ओके, अब इसी इक्वेशन के अंदर अगर तुम फॉरवर्ड बायस लगाओगे, ओके, इसी इक्वेशन को मैं लिख सकता हूँ ID इक्वल्स टू IS एक्सपोनेंशियल Q। अब मैं इसको Q को नीचे ले जाऊं तो ये हो जाएगा KT बाई Q। ओके, KT बाई Q, KT बाई Q को लिखते हैं VT माइनस 1। ओके, सो VT क्या है? VT इज जो बेसिकली KT बाई Q। ओके, और इसकी वैल्यू कितनी होती है बताओ? We put the value here, we put the value here 1.38 to 10 to the power minus 23 joule. If I take this is 300 Kelvin, okay, and this is joule per Kelvin, and if it is a electron charge 1.6 into 10 to the power minus 19, okay, and convert this energy in electron volt, okay, or calculate this one, that will come automatically volts. So how much is coming? Tell me what is the value is coming?
25 millivolt.
25 millivolts, very good. 20, approximately 25, or you can say 26 millivolt. Okay, 26 millivolt. Okay, so Q into KT is your 25 milli, KT is 26 milli electron volt. Okay, or say voltage is 26 millivolt. Okay, now this is the thermal voltage. Okay, now what happens if you apply forward bias? So apply forward bias. So when you apply forward bias, okay, so what I can say, suppose this is my V, okay. Now depending on whether your sample is silicon or germanium, here one more factor comes, eta. Okay, for silicon it is 2, for germanium it is 1. Okay, so now when I apply this forward bias, what will happen? If this V is greater than Vt, okay, I can neglect this current 1. Okay, so I can write for forward bias. Forward bias, I can write my Ed is equals to Is exponential V upon Vt. Okay, that means if I draw my IV characteristics of a PN junction diode, okay, this is my I and this is my V. Okay, so this will go like this. This will go like this. Okay, I by V, this will increase exponential, and this is called your cutoff voltage. This is called cutoff voltage. Okay, you can say this cutoff voltage is equal to the built-in potential. Okay, wherever you have this varied potential, okay, that varied potential you can assume that is your cutoff voltage. So that cutoff voltage V gamma is 0.7 volt for silicon and V gamma is 0.3 volt is for germanium. Okay, so current will start flowing only after you apply the voltage which is greater than your buried potential. So for silicon, I can say this is 0.7 volt. Okay, and for germanium, I can say this is 0.3 volt. This is for germanium, this is for silicon. This is for germanium, this is for silicon. Okay. So a
So
exponential
cutoff voltage is the voltage जिसके बाद करंट स्टार्ट हो जाता है.
इसका करंट स्टार्ट हो जाता है और इतना वोल्टेज लगाना पड़ेगा क्योंकि इतना बैरिड वोल्टेज है ना, इतना बैरिड वोल्टेज है, इतना वोल्टेज लगाना ही पड़ेगा. दिस इज 0.7 and this is 0.3. तो इस वोल्टेज के बाद में this current gets increase exponentially. Okay, now suppose if I apply reverse bias, okay, so if I reverse bias, this voltage become negative, yes or no? If I apply this voltage and this voltage higher than this voltage and negative sign, then what I can write, id will be what? I will be what? Say id, I will be what? कितना होगा for reverse bias? For reverse bias, if V is greater than Vt, magnitude is greater than Vt, but V is negative, then what will be the value of current? Tell me, someone tell me.
Is equal to V upon Vt.
If V is greater than Vt, suppose here this is 10, this is 1000. So this become exponential minus 100. Exponential minus 100 is equal to what?
Zero.
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 Zero. This becomes 0. So you have only current equal to I equal to Is. Okay, and this is reverse saturation current. This is called reverse saturation current. Okay, this is the reverse saturation current. Means now what will happen? This current will flow like this. Okay, very negligible current will flow in reverse direction. Okay, this is the forward direction, this is the reverse direction. Current is opposite. So this very negligible current will flow, and if you keep on increasing the voltage at a particular voltage, what will happen? What will happen?
Breakdown will happen.
That breakdown will happen. Okay. So far we are not interested in this reason. Okay, we are assuming that my voltage is very less than less compared to the button voltage. So my diode will give you only constant current, and that current is in microampere. The current is in microampere. Similarly, this current is in milliampere. Okay, here you can put volt. Here also you can put volt. Okay, this is microampere. Here also you can put volts. But you have to understand these scales are not same. Okay, this is the compensated scale. Here we are voltage 1, 2, 3, 4, 5, 6, 7, 10. Okay, here you have a voltage 0.1, 0.2, 0.3, 0.6 up to 1. So ये scale और ये scale same नहीं है. I have drawn same scale, but both scales are not same. Okay, you have to understand that one. So you can say that scale is multiplied by 0.1. Okay, so this is your compensated scale. This is called compensated scale. Okay, that scale is not same in both sides. Okay, so this is my IV characteristics, and I'm interested in order to deal diode, I need this IV characteristics. So you have to remember one thing: when diode is forward bias, it gives you exponentially increasing current. Okay, exponentially increasing current, and when it is reverse bias, it gives you negligible current or zero current. Okay, now here you can see the current changes with voltage. Current is changing with voltage. That means your diode do not have a fixed resistance. Okay, your diode do not have a fixed resistance changing. Every point voltage you have different current. Every point you have different current. Every point you have different current. Okay, that means your resistance is changing. Now, diode. Okay, so there are three models. Okay, one is called your ideal diode model. Okay, the second is called your constant voltage model. Constant voltage model, and third is called your piecewise linear model. Piecewise linear model. Okay, so you have, in reality, this is your IV characteristics. Okay, this is your IV characteristics. Okay, V I microampere, milliampere, just to show the scales. Okay, volt. But if you say this is my IV characteristics, okay, then circuit में अगर कोई करंट फ्लो कर रहा है तो क्या होगा, इसका रेजिस्टेंस बार बार चेंज होता जाएगा. हर करंट के लिए इसका रेजिस्टेंस अलग होगा. That's why it is a non-linear device. Diode is a non-linear curve. Okay? It's a non-linear curve, and your diode is a basically non-linear device.
So last, can you explain why it is non-linear?
Because IV characteristics is not linear. No? IV
Oh.
characteristics is not linear. So your diode is not a linear device. It's a non-linear device. Okay. Now, non-linear device के लिए you cannot use
Alusha,
हाँ.
voice is breaking.
So I'm saying with this IV characteristics, okay, you cannot tackle diode in the circuit. Okay, so this is actual characteristics, but we will do some model which will approximate this IV characteristics, and using that model only we will try to deal or tackle diode in the circuit. Okay, that tomorrow I will discuss. Okay, so here I'm stopping. Tomorrow we'll see
अरे थर्ड मॉडल क्या है?
piecewise linear model.
ओके सर.
Piecewise linear model. बड़ा आसान है. कल से हम शुरू कर देंगे डायोड को. आज डायोड का इंट्रोडक्शन हो गया. कल से हम डायोड को सर्किट में डील करना सीखेंगे. ओके, सो थैंक यू.
Thank you, sir.